Awesome. Okay, so welcome. This is week 3. We had the introductory session. The last session, just because of logistics, was actually, I think, 3 or 4 weeks ago. It was a little while ago. And we went through some of the notebooks. We looked at representations. We're alternating between doing the practical, hands-on, more modern content with the textbook, which is the more traditional computer vision content. So today's chapter 2 of the book. It's uh it's a very traditional book so far, which is interesting because for me, almost all the content in this chapter was new. So even though I've done a lot of vision models and done deep learning, whatever, some of this more basic stuff was completely new. And so our next session will be, again, just by logistics. I think it's in 3 weeks, the second Saturday in August 9th, I think it is. And that will again be workshops. So the homework for that will be looking at potentially the YouTube videos and slides and the Python Jupyter notebooks. So for today, we're going through the Selesky book. We're looking at the second chapter, which has 3 main sections: geometric primitives and transformations, photometric image formation, and stuff about the digital camera. So before we just kind of dive in, this is a pretty long chapter. I think it was like 70 odd pages. We're not necessarily going to cover everything. I've read through the chapter, um, sort of tried my best to understand the material. I'm hoping that some of you actually have more like robotics or computer vision background, and you can help explain some of this stuff for us. But I just wanted to see, kind of like by show of hands, how many people have actually looked at the chapter, at least skimmed it over, seen the topics. Okay, good. And then are there any particular topics or questions that you guys would like us to spend a little bit more time on today? Some of the obvious things for me are the homogeneous coordinates, projective geometry coordinates, which I had never seen before. Quaternions I'd heard of before and spent a little time trying to wrap my head around that. And then I don't know if there's any other topics. So any specific requests? All right. No special requests. All right. So then let's just go through this. And again, the hope is that this will be a dialogue. Let me clear this. The hope that this will be a dialogue, and um, and collectively we can work our way through this better than individually, and also hopefully as a group thing we can keep each other motivated to keep going. I know I have a lot of books that I'm halfway through, so when we do it together, it helps motivate me to keep going all the way. All right, so for me, I felt that the most relevant technical content was mostly in this first section, the geometric primitives and transformations. Some of this other stuff was very good background information, but it didn't necessarily feel like I was going to be necessarily using it if I were doing, you know, more machine learning types of projects. So here's the different sections that we have in here. It talks about the primitives, how you represent points, lines, planes, things like that. And then it gets into different kinds of transformations with a drill down into rotations. I hope I am. Oh, is it not? Uh, what is going on here? It's in the Zoom. So why is it not getting? Sorry, logistics.
This one needs to be in the Zoom too.
I thought I wasn't. Oh, Jesus. No, that's what it is.
You want your whole
Yeah,
screen?
yeah. All right, sorry about that, guys. All right, I think it's early onset dementia, but we're okay. Okay, so there's three main sections in chapter 2: the primitives and transformations, image formulation, and digital camera. As I was saying, I think most of the technical content that's relevant towards machine learning is in this first of the three sections on the primitives. So we're going to talk a little bit about how the data is represented, and we'll get into transformations with a focus on rotations as a drill down into there. And then 3D to 2D projections. Ultimately, if we live in a 3D world and you form a 2D image, that's a 3D to 2D projection. The other two sections I thought were useful for understanding some of the background and some of the complications, sources of noise, but not necessarily super relevant if you're not someone who's trying to fix those problems, right? So if you're doing astronomy and you know you have an imperfect lens and you want to fix it to get the most accurate measurements possible, you need to understand all these phenomena. If you're just saying, hey, I have a bunch of images, let's say they're satellite images, they're not perfect. There are going to be these various distortions. But if you can't fix them, then at this point, you're just doing machine learning on what you have, or somebody else has tried to fix them as best possible, and you're doing machine learning on it. So, yeah, so I thought it was very interesting. I learned a lot of stuff, but not necessarily stuff that you'll be using, say, in a robotics project. All right, so let's get into the first section. This is a pretty popular book. I thought it's kind of interesting because it's like a little bit of like almost like a reference book as opposed to a teaching book. There's a lot of material that it seems to cover without really trying to teach it to you, just sort of like half assuming you know it, half not assuming you know it, or whatever. And so one of the things is these homogeneous coordinates. So homogeneous coordinates, you see them in the book very quickly where it adds an extra dimension. So in two dimensions, you have three numbers. In three dimensions, you have four numbers. You have a four vector representing things. And the explanation that I saw is that basically this comes from projective geometry. Let me just check the chat real quick here. All right. I don't know if anybody else here has more background, wants to try to give a basic overview. Can I pick on you? All right. This has a little juice, I think. Would you pass the
Thanks. Yeah. So as a little background, I worked for like 5 years in autonomous driving, and prime was like image-based computer vision. So what we did is like you have an object and you try to track it. So we go from 2D to 3D, and homogeneous coordinates were used to basically represent your transformation between your 2D image to your 3D points in like one matrix. So when you think about like we actually had the opposite problem. So you go from like 3D to 2D, like the same transformation, just reverse. You go from like a point into your image, and there you need the rotation and translation of the camera compared to your reference frame. And this rotation and translation would be like hard to present in one matrix because you'd always need to have like a plus addition pretty much. And with homogeneous coordinates, you have the advantage of having one matrix that you can derive and work with. So that was like the big benefit that we used in the past. So that's kind of like the one thing that we used it for. And then like additionally, the nice thing is like when you want to work in classical computer vision, you want to represent the horizon at some point. Because like sometimes you need to know where the horizon is, and like you have some assumptions like that you can use for distance estimation. So like horizon is some really tricky thing. And like with homogeneous coordinates, you can just like in your image say, okay, horizon is here, and then you can transform it back into 3D and it works, which is really nice. So in a nutshell, that's pretty much where I used homogeneous coordinates before and where they were really were a big advantage to us.
Awesome. Thank you. So, yeah, the easier way to think about from the reading that I did, the easier way to think about these projective coordinates is to start with just the two-dimensional case, not the three-dimensional case. Okay. So if you imagine you have a plane and you're just describing points with an XY coordinate on it. All right. So let's just say this is a plane that's like a projector screen. Okay. And you could all right, thanks, Ryan. All right, we're going to go through all the logistics today. Um, so I was saying that you can think of it as like um, you have a projector. Imagine just like a regular projector. You can have the screen close to it. You'll have a very small image. You can have the screen very far away from it. You'll have a larger image. So the coordinates, just in terms of like inches, are going to be larger numbers the farther away, but they represent the same exact 2D image, whether you have the projector screen very close to the projector or very far away. All right. And you can convert between the screen being, say, 1 foot away versus the screen being 2 feet away by doubling all your numbers, essentially. Okay. So it's just a scaling factor. The way that projective geometry represents that scaling factor is sort of the reciprocal of the distance. So you and I might intuitively think to represent it as like I was just saying, 1 foot away, 2 foot away, but it would be more like 1 and 1/2. And what that means is then, as you keep going farther and farther away in the limit as you approach infinity, that scaling factor becomes the number 0. So the point I have at the bottom of the slide is that if you have, say, train tracks and they're going off to what's that called? The perspective with that point, I don't know, vanishing point, whatever that is, right? That point doesn't have some weird coordinates with a limit with an infinity in it. It has just a regular set of coordinates. It has a 0 in the scaling factor. So it has an X, a Y, and a 0. And it turns out that all the math that you would do with objects that are not at infinity, you can do the same exact math with that 0 in there. Everything just works. So that's particularly convenient to be able to represent points at infinity and not have to do any special casing or weird limits or, things like that. Ultimately, the reason, yeah. Yeah. Just so the people in the Zoom can hear, we need to.
Thank you. So yeah, just to add a bit to that. So you can think of an image like you have an image plane, right? Where you like your pixel coordinates live in. So like you can think of this usually homogeneous coordinates as like image plane is like number one. And then when you go further, it's nothing else than like just extending. So you see something in an image, it said like set coordinate one in homogeneous coordinates. And then when you want to project it into real world, you just say, okay, now it's not like distance one away, it's distance like 10 or 100 away. And like everything just scales up. So it's like it's a very simple mathematical trick to basically just say like the same thing that you see like far away in like reality is like 10 meters away. The same thing you see in the image is like normalization factor one in pixel coordinates XY. So it's just like this difference between pixel coordinates, pixel plane to like actual real world is like a smooth transition with homogeneous coordinates pretty much. If that makes sense.
All right. So if you're interested in this and would like a little more information, I found that this YouTube video, I'll share the slides. You can have the link. Um, but the voiceover's pretty dull, but the content I thought was pretty good in terms of explaining things. And the same thing we can do with just 2D images being on a projector screen closer or farther. You can do the same thing with 3D images. It just doesn't have a very good intuition for because we can't like see 4-dimensional spaces, but it's the exact same concept where you just have a scaling factor. The farther, which doesn't really make sense, the farther things are, you have a scaling factor. Okay. And if you remember, if you know your linear algebra, in a vector space, you can multiply by a matrix. And what that can do is that can rotate things, and that can also scale stretch things, either proportionally or not proportionally. But that's all you can do with a matrix multiplication. When you add this extra dimension, what ends up happening is you can also, have this on the previous slide, you can also do translations and you can do projections through matrix multiplies. The key one being translation. So an object that just simply moves to the side can be represented by a matrix multiply. The benefit of having everything that you typically want to do in a transformation represented by a matrix multiply is that you can now chain these transformations. And it's just a series of matrix multiply. So when we're talking about fast calculations, if you want to do a rotation and a translation, if you do it in just Euclidean coordinates, the translation needs to be done as like this separate add process. Whereas if you have matrix multiplies, then you could have 16 different transformations. Doesn't matter what they are. Translations, rotations, other things. And depending on how you're doing things, you can do very fast, or you can even pre-compute by multiplying a bunch of these matrices together, and then you just get one single matrix that represents the entire set of transformations. So that's just a little bit, didn't go into it too deep, but a little bit in terms of the homogeneous coordinates. Any additional color or questions? Yeah. Yeah, it's an observer, but it's also like the distance from the observer. And what that does is it gives you sort of this extra degree of freedom. So in this video, because one of the things I was thinking is how can you do translation as a matrix multiply? Okay. And I'm just going to say this, but I don't know if it's going to make sense me saying it without like playing the video. But basically, in 3 dimensions, you can do a shear. So you take an object and you just tilt it or whatever. Um, and that's just a matrix multiply. But when you project that back down, then where it lands is not where it originally started because you did a shear. And so the way he explains in the video is essentially you can think of it as a change of basis. So you start with a projection with like a vertical z-axis. And if you tilt the basis for your z-axis and then project it down on your normal, then you're going to end up like okay. And so that's really what you're doing is you're just applying a change of basis. And one of the change of bases is just tilting your z-axis. And when you do that and you say my coordinates are still, 1 comma 1 comma 1, but with a tilted z, what that means in your normal XYZ Euclidean coordinates is something that shifts to the side. Any other questions, comments? All right. So, um, going to briefly go through some of these other concepts that they show. For the most part, we're going to see that they are representing all of these in homogeneous coordinates, which means that when they talk about them, the vectors have a little squiggle over them. Okay. The base homogeneous coordinate is if you just take the xy or the xyz and you just add a 1. And so in the notation, you'll see that they have a horizontal bar over. So x bar means you just added a 1. X squiggle means any valid coordinate in homogeneous coordinates. Okay, so we can go into it if people have questions, but kind of super fast. You're going to need to have primitive objects and concepts. So starting with 2Ds to be a little simpler, a point is just 2 numbers in 2D, or it's 3 numbers if we're using the homogeneous coordinates. A line can be parameterized many different ways. If I think back to what was it, high school geometry? If you remember, they had different formats. They had point slope format and whatever y equals mx plus b. They're all valid. There's just different ways of using numbers. So in 2 dimensions, you always need 2 numbers in order to represent a line. And so there's just different ways. So one of the ways that they parameterize lines here is they say if you take the dot product of I forget the name of it, but x bar, if you take the of a point x bar with a homogeneous coordinate L squiggle, then that basically defines a specific line. That's if you say that dot product must equal 0, then that defines a specific line that's perpendicular to the direction of L and a specific distance away from the origin. So it uniquely defines a line. And that's a very convenient way. Again, it's amenable to matrix multiplies, and it's very compact. They also talked about conics. I didn't really write anything down there, but you can easily represent conics using a quadratic equation with dot products, with multiplies. When we go to 3D, which is mostly where we actually care in the real world, you have XYZ for your regular Euclidean coordinates, or you need 4 numbers if you're going into homogeneous coordinates. And now, if you take x bar and you dot it with a vector in 3D, you don't get a line. Now you get a plane. And this is the plane that is all perpendicular to that particular vector. So that's the normal vector that defines sort of like if you have a sheet of paper, the up direction. And then this equation, x dot m squiggle equals 0, will define all the points in that plane, again, perpendicular to m, a particular distance from the origin. You can represent lines in 3D, but they say it's less elegant. There's no super, super great way. You can use 2 points to define a line in 3D. You can use 2 points specifically in 2 planes because when you use 2 points, you have, what is it? 6 degrees of freedom, and that's actually more than you actually have for a real line. So 2 points in 2 planes reduces it, and they don't even explain it, but they say there's also this thing called Plicker coordinates. So I don't think we need to spend time on it, but just know that you can define a line, but it requires a little bit more work. You don't just get one very short, easy equation. And then finally, they did 3D quadrics, which I did not spend any time on trying to focus. Just good to know. All right. Any questions, comments about these primitives? All right. So moving on, they spent a time talking about transformations, which are very commonly performed. These are the most common ones. And what I did is I just copied the chart here. The way the chart works is at the top of the chart, towards the top of the chart, any of these transformations, if you see the column preserves, it preserves what it says there and everything below it. So a rigid transformation preserves lengths, angles, parallelism, and straight lines. So anything that's a certain length before will stay the same length after. Any angle before will be the same angle afterwards. Any 2 lines that are parallel will stay parallel after, and anything that's straight will stay straight. Okay, so the only thing it doesn't preserve is orientation. So that's why the mnemonic they have for it here is just something like a little square that's rotated, right? Similarity is more general. Okay, it doesn't preserve length anymore, so something can get bigger, it can scale. An affine transformation then doesn't even preserve angles, but things that were parallel stay parallel. And then the final one, projective, it doesn't preserve any of the above. The only thing it preserves is that if something was a straight line, it stays a straight line, but its length, angle, what it's parallel to, all of those things can change. So the book goes into more detail and it talks about these are the matrices that you can use to multiply all of your points or whatever by, and ultimately then you will get the result. There's also this comment down here that if you look, a bunch of these are not square. So they're convenient one-off transformations. But if you want to chain them, you need to use square transformation matrices. Okay. So they say anything that's a 2x3, basically you can turn into a 3x3 by adding a third row. And they show you here that it has to have all zeros and a 1 in the bottom row. All right, I'm checking my chat here. So I don't know how long ago there's a question about, can this translation rotation be used to correct perspective wide angle images to perpendicular images in real world computer vision? I'm not sure I fully understand this question. There is a section later that talks about certain kinds of corrections. These are all linear transformations. So most of the corrections we're going to talk about are definitely non-linear. So like, lens corrections and things like that. So I don't think that this set of transformations would be sufficient. But these are the types of transformations where you have an object and it's rotating, or you have an object and it's just moving, and you're tracking it, those kinds of things. All right. So we can do the same thing with these 2D objects. that we do with 3D objects. Oh, sorry. There's a couple other things they mentioned briefly. Stretch squash, planar surface flow, bilinear interpolant. You can do the same thing in 3D, and basically we see the same thing here. It's just you have different sized transformation matrices that then operate on our four-dimensional homogeneous coordinates now in 3D, but it's the same concept. Again, translation, rigid Euclidean, similarity, et cetera, et cetera. But the one thing we're going to do is we're going to drill into 3D rotations because, was that a question? Yeah. Yeah, so the question is, what would they look like in 3D? That specifically says if you read the details of the caption that the icon is not fully representative of a 3D object anymore, but it's again just to give you the concept. Um, uh, translation is motion, but again, it has 3 degrees of freedom. It can move left, right, up, down, forward, backwards, right? Rigid is rotations. Similarity allows for um, stretching and shrinking, right? Uh, affine allows skew, and then projection is the hardest one, which then it even breaks parallelism. So I think it says in here mnemonic. You can imagine that it's a cube, even though they've only drawn a square there. What's happening? But I'm not sure how else to, like, for me, like sometimes people have a geometric intuition and sometimes you don't, and I'm not quite sure how to make a difference with that. Yeah, yeah, yeah. So the homogeneous coordinates, when you do one transformation, it is not necessarily any easier or any faster. Okay. But all of these are matrix multiplies. So this means you can chain any number of these types of transformations in any order, and it's just a string of matrix multiplies. If you didn't use homogeneous coordinates, then translation would be a sum. It wouldn't be a vector sum. It would not be a matrix multiply, right? Rigid rotation would be a matrix multiply. And so, like, you can imagine if you did a translation, rotation, right? Then you'd be alternating, adding and multiplying. And if you just naively tried to simplify that, you would get a whole lot of terms, right? Because you'd start having to add things in, and then when you multiply, you have three things that you're multiplying and summing, and then you add more things, and so you could come up with a simple collapsed formula for add vector A multiply by matrix whatever M, add vector A2 multiply by, you could expand that out and you could figure out a closed form formula, but it'd be a real pain in the neck. If you did with these homogeneous coordinates, if you did 5 rotations and 5 translations alternating, it's just 10 matrix multiplies. And matrix multiplication is associative. You can combine those matrices in any order you want. And ultimately, it'll reduce down to one single matrix multiply. So you could pre-compute all 10 of them and save that off. You can still do that with the other, but it would just be a real pain in the neck. Yeah. So a lot of this discussion, as far as I can tell, I am not the expert. As far as I can tell, really is about how do you get this in a convenient format? How do you get this in something that can be computed very fast? If you're doing computer animation, ultimately, you don't just want to know something's theoretically possible. You want to know I can calculate the scene and I can do it very quickly. So if you have this complex object that's made up of, thousands of polygons and it translates and then it rotates, it'd be nice to just say, oh, I can have this one matrix multiply and apply that to all of the vertices or whatever, instead of saying, oh, I'm going to do this very complex series of operations. The question is there a limitation on the matrix degree? So for three-dimensional objects, you just need that one extra dimension. You need the fourth dimension, and then all of these transformations can be encoded as straightforward matrix multiplies. The weird thing, of course, is now that points are no longer unique, right? So in our 2D case, we talked about the projector screen. So the point 111 is the same as the point 222 is the same as the point 333. So at some point, you're probably, when you're done, you might be converting it back to Euclidean coordinates. But the good news is that by doing this, all the intermediate operations can be very fast, and you're just doing one conversion at the end. All right, so we have an entire section devoted just to rotations because rotations in 3 dimensions are not as simple and pretty and easy as we would like them to be. Rotations in 2 dimensions are very easy. Okay, you can just have the amount of the rotation, and if you're doing it in radians, then every 2 pi it repeats. And you can add and subtract rotations, right? So if you rotate whatever 45 and then you rotate another 90, that's the same as rotating 135 degrees. But in 3D, it's not as simple. And in fact, you have this problem that it's not commutative. So if you have one rotation and then a second rotation, if you change the order, you do the second one first, you do not end up in the same place. And so things get pretty ugly. So they say that one way you can talk about it is if you just have your X, Y, Z axes. If you fix the angle, the axis of rotation, such that it's only a rotation around X, a rotation around Y, and then a rotation around Z, you can define any rotation. Turns out there's another form of it where you rotate around X, rotate around Y, rotate around X, and that also, even though you don't actually ever rotate around Z, you can do an equivalent thing, and you can define it any rotation. It says, this is a terrible idea. We're not even going to tell you the formulas for this because we don't want you to use it. Okay. The issue with rotations has to do with smoothness and what happens when you kind of go around the circle. Okay. So super simplistically, if you just look in 2D, if you said, I'm going to represent all rotations in a finite range as rotations between negative pi and positive pi. Everything's great when you're near 0. Everything's great when you're near pi over 2 or whatever. But when you get close to 3.14 or whatever, all of a sudden you have this problem that there's a rotation very similar to you, but the only way you can represent it is with a number that's very far away. Okay, so at, pi minus a tiny amount epsilon, there's a rotation very close to it that's pi minus 2 epsilon. Oh yeah, you're fine. But you go the other way, since you're not allowed to go past pi, all of a sudden you wind up at negative pi. And so you have to all of a sudden have a completely different number. Okay, that's the problem that we're generally trying to avoid. In theory, right, like we can come up with some scheme like, oh, let's use numbers between 0 and 2 pi, and we'll do modulo 2 pi. But that means that you're constantly having to interject this correction business. it gets even wackier in 3 dimensions. So they say that a common representation is this axis angle thing. And so they didn't say it in the book, but there's some Euler theorem, whatever. Euler proved like 80 million things in mathematics. And apparently, one of the things that he proved is that any set of rotations in 3D can be broken down to just simply one axis of rotation and amount. So it'll never require more than that. Okay. And so if you know the vector, that's the axis of rotation. That require a vector in 3 dimensions requires 3 numbers to specify. Okay. And then the amount of rotation angle theta. So it requires 4 numbers to represent this. There's 4 degrees of freedom in this rotation. And that's that ultimately ends up with this Rodriguez's formula, which is how you basically convert the concept of an axis vector and an angle into an actual 4x4 matrix so that you can do the matrix multiplies. Okay. The other thing that they mentioned in the book is unit quaternions. They didn't really explain it. I did a little bit of reading on this. But before I kind of dive in, is there anybody here who's familiar with quaternions that can help give a little bit of background as to what they are or how they work? All right. So I read through the Wikipedia page, and there's a lot of information on there that's, as often is the case when I read technical things on Wikipedia, there's parts of it that go way over my head, right? But there was a section in there that I found particularly useful. So basically, the way, I hope I have this right, the way I now think of quaternions is it's the same thing as this axis angle business fundamentally. Okay. A quaternion defines the axis of rear rotation and the amount, but it's just parameterizing it slightly differently. So in the same way that when I took, what was it? Algebra 2, whatever they called it. I don't know. But like you did polar coordinates and you had like r and theta, and you can represent any given point using an r and a theta instead of using an x and a y. Okay. So what quaternions do is they represent the the axis and the angle, but slightly differently. And one of the things in particular about it is that the they call them unit quaternions is because the norm of this is always 1. So if you have the 4 numbers, I don't know exactly what they're called. I'll call them A, B, C, and D. Okay. A squared plus B squared plus C squared plus D squared always equals 1. All right. Just like the Pythagorean theorem, kind of, right? And that restriction actually causes it to have some very convenient behavior. This normalization thing ends up being very convenient. So first, a little bit as to why quaternions. Okay. They're easy to compose or invert. So if you have a rotation represented by 3 quaternions, you can combine them. There's a shortcut formula that's a very fast way to combine them. Okay. That's not necessarily true for all other representations. And so the other thing about it is that this thing I was talking about. So with quaternions, any rotation that is close-ish to a given rotation will have a numerical representation that's close-ish to the representation. So all, 1 or maybe, several of the numbers will be off by a small little epsilon, but you'll never have the problem that, oh, I have this rotation, but I just sort of hit like the international date line, and now I have to add 360 in order to get like the next little bit over. Okay. So that's the main plus. And so it says in the book that you can use it for pose, you can use it for pose interpolation, and you can use it for spherical linear interpolation or slurp, which happens a lot if you're trying to like interpolate between two positions, interpolate between two rotations. So I didn't have time to make a slide for this, but I'll give you the gist of what it talked about in the Wikipedia page, which I thought was kind of cool. So if you think about just the unit circle in the 2D plane, we can represent a rotation with one number theta. And no matter what range we pick, there's going to be a point where we have the max value and the min value slamming into each other, and it's going to be a problem. All right. So let's say we just represent it as a number between 0 and 2 pi. The problem is that 0 and 2 pi are really close to each other, or when you get close to 0 and close to 2 pi, those two values are very close to each other, but their representation is very far away. Imagine if for the unit circle, you went to Cartesian coordinates and you had XY coordinates. It will never be the case that a point that's near you on the circle has a radically different representation. It's always going to be very smooth. Okay. And that's what that extra degree of freedom gives you, is as you're moving around this circle, right? As you start, the way I think about it, like typically where, 0 degrees to the east, y is going up and x is going down. But then we have this trade-off where y starts going down as x continues to go to -1. And then what happens after that is then x starts going back up and y is, approaching -1. And so there's this smoothness you have because there near the cardinal directions, one of the coordinates is changing, but the other one isn't. And so it's like the other one's resetting to be able to take over when this one gets into a tough spot. That's the same thing that happens with quaternions. And so the example in the Wikipedia page is, this is a little bit of a tough example, but I could try pulling up the Wikipedia page. But imagine that you are doing 3D rotations, but you're only doing rotations limited to where the axis of rotation is in the XY plane. Okay, we're going to expand it, but initially we're going to start with just rotations in the XY plane. So in that case, the axis of rotation can be represented by the direction, because it's just in the XY plane. Okay, it can just be represented by the direction. Okay, so that's like your regular theta or whatever in the plane. And instead of representing the amount of rotation the way you might normally think to do it, okay, let's say we now enforce this criteria that the x and y coordinates on the circle plus the amount of rotation, okay, if we square those three together and they have to sum to 1, then what are we going to get? We're going to get the points on the unit sphere. So if you say x squared plus y squared plus z squared equals 1, you get the points on the unit sphere. And so essentially what we're going to say is that the North Pole represents 0 rotation. And as you go towards the equator, it's more and more rotation. And then what ends up happening is when you go below into the southern hemisphere, you now, I'm getting a little bit confused. But ultimately, what's going to happen is that the rotation amount is going to decrease until you get to the South Pole. And so there's this weirdness that you can represent 0 rotation as either the North Pole or as the South Pole. Um, but there is this smoothness that happens where any rotation that's slightly different is just going to be a point near you on the sphere, on the surface of this sphere. And so and the X, Y, and Z coordinates are going to be slightly different. So I don't know if I did that justice, but in the same way that I said 1D going from theta to x squared plus y squared, this is now doing it going from 2 to 3 dimensions, x squared plus y squared plus z squared. Real quaternions, we now relax it so that the axis of rotation doesn't have to be in the xy plane. It has 3 dimensions, but the concept works exactly the same. It's now going to be a unit 4-dimensional hypersphere that you're on the surface of, and it's going to have the similar properties. And so that's where this whole business comes in, that everything can be represented as, like, say, a 30-degree rotation with this axis, or if you flip the sign of the axis, it's a negative 30-degree rotation in the opposite direction. So there's always exactly 2 representations. This normalization business is the thing that keeps you from running into that problem of, oh my God, I'm at 2 pi. Now I need to suddenly jump back down to 0. All right, so that's a whole lot of explanation. If any of that made sense, great. Yeah, reaction. Yeah. Yeah. Uh, um, I'm not going to try and repeat the question, but sorry if I had a little more preparation, I might have created more slides, and then hopefully you would have been so lost. What we're really ultimately talking about here is how to represent just rotations for now, okay? And what is the most convenient way? None of these ways of representing a rotation are wrong, but they have inconvenient properties, okay? So this axis angle and the unit quaternions are both designed so that if you compose rotations, we can fairly quickly do the math to figure out what the resulting net rotation looks like. Quaternions potentially for some people are a little bit easier to work with, and that's why at the very end the author of the section, the author says, hey, like different people have different preferences. I personally prefer quaternions. Okay. So it's, for a terrible analogy, it's like the whole business of Cartesian coordinates and polar coordinates. If you're trying to draw a square, Cartesian coordinates are much more convenient. If you're trying to draw a circle, polar coordinates are much more convenient. Neither of them is right or wrong. They just are more compact and easier to work with than others, right? So, it's also a little bit like what is that stuff where for the complex numbers you can do e to the negative I theta or whatever, or you can do the more Cartesian representation, cosine theta plus I sine theta. When you're adding numbers, it's much more convenient to have it in the one. When you're multiplying, then you'd rather have e to the I theta, because then you can just add the exponents, right? So this is just talking about how do we have different representations, and the specific example they talk about in the chapter is this idea of gimbal lock, where if you're really unlucky, you like with the old-fashioned representation, you wind up at like -90 on 2 of your different gimbals, and you're trying to go to the next adjacent direction, which is +90, and it's a discontinuity. It's not a smooth thing. And you're, I don't know, but apparently like real flight systems would hang So you say, I want to just go a little more, and the system will be like, I'm not sure what to do here. So I don't know the details, but they say that gimbal lock was like an actual problem. If you have quaternions, you will never run into gimbal lock because if you want to just turn a little more, it's always just a slight difference in the numbers. You'll never run into the situation where you want to turn a little more. Oh, okay, now you got to add 2 pi to some number and renormalize it and whatever. I also saw that there's with quaternions in the real world, you have floating point rounding quantization errors and you have measurement errors, and that this always if you have some small errors, then what you do is you just renormalize it, right? You square everything, sum it, and if that's 1.1, then you just divide everything by 1.1, and now you're suddenly back at unit length. Whereas it's not as obvious what to do if you use axis angle and you've got accumulated rounding errors, floating point errors. It's not as easy to correct. Hope that answered a little bit. Okay. All right, thanks. So again, this is information, depends on the kinds of projects you're going to do. If you do robotics, there's going to be, I think, chapters later on where we talk specifically about um what is it? SLAM or whatever, simultaneous localization and mapping. Okay. You need to represent the objects that you see with coordinates, and you need to do math on them because you're moving, they're moving, whatever. Okay. And so this stuff is going to be in the background of all of that. If you just do classification, dogs and cats, I don't think we're going to use any of this stuff. So, all right, let me just do a time check here. All right. So as I said, this is the main meat of what I thought the technical stuff. I'll go through the other stuff, but it won't take us nearly as long for the other stuff. Yeah, another question? The question is there a relationship between Rodriguez formula and the unit quaternions? Yes. I'm not the best to explain it. Ultimately, all of these things have their equivalences because they all represent the same real world 3D rotations. Okay. So ultimately, these quaternions are just a slightly modified form of this axis angle business. And at the end of the day, you have to convert them to a 4x4 matrix in order to calculate that particular rotation. So, from what I understand from the book, Rodriguez's formula ultimately is involved when you compose rotations with either of these formations, and this whole business of how we represent the quaternions, it ends up a lot of terms cancel out, and so the formula for doing 2 quaternion rotations consecutively ends up not having a whole lot of terms. If you remember from algebra, when you multiply 2 binomials, it's FOIL, right? First, outer, inner, last. You get 4 terms. You multiply 3 binomials, what do you get? I think you get 8 terms, right? And it just keeps growing. So if you had a formula like that and you composed a whole bunch of things, all of a sudden you have 2 to the n terms, whatever, right? But if you're really lucky, and let's say you have something like x plus 1 times x minus 1, you still only have 2 terms. It ends up with x squared minus 1. If you then multiply that by x squared, I'm making stuff up, but x squared plus 1, right? Now you just have x to the 4th minus 1. Your number of terms is not growing as you keep, doing these. So that's what these convenient formats allow for, is that because of this convenient representation, the formulas don't just keep exploding combinatorially as you compose more and more of them. That's what makes them convenient ultimately. All right. I don't have too much to say about 3D to 2D projections other than, wow, I never thought that projecting a 3D scene to 2D could be so complicated. Um, um, the the geometric thing that I think that I was taught was sort of this perspective one, um, where you divide things by their z component. But since each point maybe has a different z component, my impression is that this is the slowest way. So if you had a scene that was represented by 1,000 polygons, however many points, thousands of points, every point needs to be divided individually by by their z component. Okay. These other things are faster. So you can imagine the first one, the orthographic projection, we just drop the z component. We just zero it out. That's a heck of a lot faster than having every point individually divide their x and their y by their z's. I think x, y, and w by their z values. Okay. And so then there's the scaled orthography and then the paraproject perspective. So it may be hard to tell from this scene. You may need to go back to the book and zoom in really big. But if you look, what you'll see is that this perspective one is really simple, where you just take each point, and if we're projecting it to this close by plane here on the left, we just draw a line between the observer, the camera, whatever, and we project things along that line. And that's what dividing by z does. It gives you this perfect projection, but it's expensive. And so in this orthography, if you can see, it might be a bit of an eye chart, but there's this line here, and every point, effectively, it's as if every point were moved to this same line. It's not technically what you do when you just drop the z, but when you drop the z, the distortion, if all the points had the same z, there's no distortion. But if all the points don't have the same z, then you're treating them as if they all had the same z. And so it's the equivalent to pushing all the points to this line and then projecting that line to the left. And then like the scaled one, you can see, oh, each object can have their own defined line. So they're slightly distorted within the object, but inter-object, they can have their own, whatever. So that's what these different projection techniques are. And the book doesn't say it, but my impression was that these other methods are faster than doing the full perspective thing. Yeah.
Thank you. Yeah, so another quick comment to that. If you go back to the other slide, I think it's pretty easy. Like you always see the line on the left side. That's pretty much your image. So like you have like some 3D real world scenario. Like let's say you like bird's eye view look at it, and then you try to get like your image coordinates from your 3D world. And then you actually see, okay, it's like just a projection to the line, to the imager, and then you get your pixel coordinates. So that's like the fundamental thing that we're doing here. Honestly, in my experience, we always used the perspective. There was no, like a division was not super costly, so it was fine. Yeah.
Can I get some feedback on this intuition? So when I'm hearing these things, one of the things I think about is a literal projector, where if you are projecting the image low and you can see that there's that skew, and then either the projector used to have this manual knob, so that way you can actually turn it or adjust it, so you don't have to physically move the projector, right? So it's that variable that you're adjusting for, and that change in that skew. And then when we're thinking about it in the quaternion is when I got lost or a little bit confused earlier. And you mentioned the gimbal example. The practical application that came to mind was like the GoPro 360, right? So when we're talking about those variables, being able to compensate for all of the positions of the many cameras, or maybe two, I don't know what that GoPro has. Those are the those parameters that help compensate for those differences in skew. So that's how I kind of think about it intuitively as a non-math person.
Yeah, thanks for sharing that. So when you have a projector, the reason why you need to adjust for skew is because ideally you want the projector pointed, old projectors. You want the projector, um, I don't know how to say it. I'm just going to say perfectly parallel, the lens of the projector to be perfectly parallel and coming at your screen. If for some reason the projector isn't perfectly parallel, so say it's on a table and it's low, then what's going to happen is you're going to get a trapezoid on here because it's not parallel. And so there's an adjustment for that. This is a slightly different scenario where we're saying we assume that we are perfectly planar, that the lens is perfectly parallel to our camera, but it's just how um how quickly can we do the calculation of where all those objects fall on our um image plane over here on the left. And so one point is don't worry about all these other things. Division's not that cheap, so we're just going to use full project perspective. And then that's just like if you ever took art class, that's what they taught you to do. Then if that's the case, then just ignore all this other junk because you don't need it. This one's the best. It causes the least distortion. And if you have the compute to do it, then just don't even worry about the other stuff. But my impression is these others, the reason why some people did them is because they were faster. Okay. Yeah, so we haven't really talked about motivation of when do we use these transformations? When do we use projection? When do we use whatever? And since I'm not a computer graphics or robotics or whatever type person, I'm actually not the best person to try to give you examples to motivate when we do all these. But you can certainly imagine. Oh, I got a hand in the back. Yeah, please.
Okay, hi. So my background is biochemistry, and actually, so about 10 years ago or so, I worked on a paper, excuse me, where we used axis angle projections to calculate how much a domain would move. So if you're doing protein structures, they don't necessarily stay in the same conformation throughout. They change, right? And so, but like the whole molecule maybe doesn't change. So you have an atom, it has an XYZ, and it goes through something and it changes positions. And then you project that basically. And so you need an axis of rotation, and that, you can do that through the axis angle through Euler-Rodriguez. Quaternions, I'm a little less, it's fuzzy, but it's, so the Euler-Rodriguez comes out as a matrix. It's a 4x4 matrix. Quaternions comes out as a straight line. It's sort of like four numbers, but it's just different math. Euler, axis angle Euler-Rodriguez is always unit quaternions, and that's all I know. But basically, those are the use cases where you're like thinking about where did my atom move in space, or where did my plane move in space? Like, is it still staying, horizontal to some fixed reference body? So that's the way to think about it.
Thank you. Yeah, and so Ryan, you were just mentioning to me the Kaggle competition um that we're working on. So right after this, we'll talk about that. But people have a sensor that people are wearing on their wrist, and they're trying to identify different behaviors based on the sensor readings. And so if somebody is repeatedly pulling on their hair, a negative behavior that they're trying to identify. And so then Ryan was saying, like, oh, so if the person's right-handed and they wore the sensor on their left hand versus if they're left-handed and they wore the sensor on their right hand, what do I have to do to make those two data look the same? Okay. So is that a reflection? Is that a rotation or whatever? So that's where these kinds of transformations come into play. And if you know this stuff well, then you're like, oh, okay, this is in 3D and this is what you have to do. And then this, you know, if you imagine it, if you had a right-handed and a left-handed person that did the thing in the exact same way, you could just transform one into the other and they'd be identical. So that's the kind of things. And then yeah, like protein folding, your protein's not going to just like whatever, like very neatly say, okay, I'm going to stand here and my first protein is always going to be at the bottom and it's always going to be facing due north, so you do have to that's where some of these things and there's even more stuff that I kind of honestly roll my eyes when they talk about like SO3 special rotation groups and whatever. But the idea there being is you do want to know the equivalences in order to say that like I would like similar loss on my training loss function for rotationally equivalent outputs. So okay, so moving along quickly. The next thing it talks about is camera intrinsics. Not going to go into a lot, but ultimately the idea is that you have an outside world and you're projecting it onto a small planar rectangular set of sensors, right? And so there's business about you've got real world objects, they're coming in on a light ray, you're mapping these things, and you can have this calibration matrix. I've heard people talk about camera intrinsics, right? And so they're saying, hey, here's this matrix K that's part of this business that lets you capture. And ultimately that has to do with, again, like, if you have a wide or a narrow angle lens and how far things are from the sensor is from the lens and all that kind of stuff. Whoops. And they talk a little bit here about like focal length. So any of you guys photographers, I'm not. I always heard people talk about f-stops, depth of field, things like that. And so this is some of the stuff that's here at the end of the section. Lens distortions. So in the real world, you have radial distortion. And so this is actually another one of those things that projectors used to have, is this barrel pin cushion adjustment. And so that's just an imperfect lens. And so depending on how far away from the center you are, things are either too far or too close relative where they should be. And in the extreme, we've all seen, I think, pictures from fisheye lenses. Your eye can immediately tell this is not a perfect representation of the real world. Things are curved and squished at the edges in a way that they wouldn't be in the real world. Right? This window is not curvy. This window was probably straight rectangles. All right. And then we have photometric image formation. So we're going to talk about lighting, reflectance, and shading, and optics. So again, I think this is less machine learning relevant. So I'll go quickly. Lighting, you can have a point light source. All you need to know is the intensity and the color spectrum. Area light sources are more complicated. It says, you can imagine a fluorescent light, like this isn't necessarily fluorescent, but this light above me being a rectangle that's emitting light in all directions uniformly. For a very complex scene, you can build an environment map. When you get to reflectance and shading, computer graphics, I think people need to know this stuff cold, right? So you can have a general reflectance function, they call the bidirectional reflectance distribution function. It basically just says, if the light comes from this angle and you're viewing from that angle, what's the value? That's very general, but to make it a little bit easier to handle, usually the main components are diffuse reflection and specular reflection. So diffuse is just like my shirt is a very not shiny object. So it's sort of emitting the same amount of light in all directions. But if you have highlights, so like the hood of the car I see in the parking lot, right? There's one angle where, depending on where the sun is, if you're at the right angle, then you're getting a bright highlight. I see people who paint stills, right? If you have a fruit bowl, there's a shiny red apple, there's going to be a highlight spot on it where the angle's just right. So you have that specular reflection. And in the extreme, if it's a mirror, then it's just basically a point, right? Exact opposite to the light source, you get virtually 100% reflection, and in all other directions, it's virtually zero. So combination of diffuse and specular, and then you can get fancier. You can get Phong shading, which would include like not just these light sources, but just the wall is also adding a certain amount of light to my shirt. So if you're going to accurately do computer graphics for that. And then it gets into, you can use ray tracing to follow beams off of shiny objects. And then radiosity is this like integral if you have things like my shirt that's more diffuse, and you just sort of sum up all the contributions from all directions. It goes into optics and says the real world is not an ideal pinhole camera. So it talks about focus, aperture, this circle of confusion. So when an object is not at exactly the right focal distance, then it's slightly out of focus. And so if you've ever seen, right, photographers, they do portraits, the background's not at the right distance, and so it's kind of blurry, whereas the subject of your picture is perfectly in focus. Goes into details. If you're trying to correct, there's apparently these 5 classic kinds of aberrations in a lens. Chromatic aberration is another thing where I remember from, what is it, high school physics, that the index of refraction is not the same for all wavelengths. It's tiny bit different. So that's how you can build a prism, because the red and the blue light will get bent different amounts because of different index of refraction. So if you have a simple lens, the different colors will actually focus at a slightly different distance, but you can build compound lenses that largely correct for them. And then there's this vignetting effect, which I had never thought about. The natural thing is that when light comes in, and if you imagine you had this giant focal area, the stuff that comes in the center is basically straight on. But if the stuff were coming in at a very sharp angle, then there's just that effect of the surface area that you're hitting is larger just because you're on an angle. And so that actually diminishes the amount of light hitting per square inch when you're not straight. It's just like solar panels, right? You want the solar panel to be perpendicular to the sun. You don't want it to be highly oblique, because then you're going to be getting less light per square inch. It's the same phenomenon where even though we're talking about, a 1-inch sensor, a 1/4-inch sensor, there's a slightly different amount of light hitting at the edges than there is in the center. All right, last section, the digital camera, going through this quickly. Here's the sensing pipeline. A little information that I didn't realize, just in terms of, you have your actual sensors, the CCDs, or the CMOS elements in a grid. And then there's actually an analog step where the signal is boosted. And then it's converted to digital. Ultimately, it needs to convert it to like an integer. That gets you your raw image, and your raw image may be unpleasing to the eye and may have some artifacts. So that's where these other steps come in, like demosaic and denoising, sharpening, white balance. So it mentions all these different factors, if you're curious, that affect your signal quality. Sampling, if you do audio, you're familiar with, right, Nyquist frequency and and aliasing. And so I particularly liked image A and image B. You can see that the true image is A here on the left, and the frequency keeps getting smaller and smaller as you go down and as you go to the right. But like this spot right here looks like it has some very low frequency elements where there's a big white patch, a big black patch. That's a complete artifact of aliasing. And so this is obviously like a test pattern, but you can see how you can have a completely artificial effect where it looks like there's this big giant whitish patch right here, and there's absolutely no such thing in the real image. So there's some things people can do to deal with that. Mostly it's high frequency, filtering out the high frequencies. Color, people who do graphic arts know all this stuff about color. This was my first dabble with color. Holy cow. There's some really gnarly stuff just in terms of we're not just thinking about color from the physics theoretical perspective. Generally speaking, all of this stuff is based on color as perceived by humans. So that's where things get gnarly is because we're not just dealing with the physics of it. And so here's this chart that shows how people actually perceive, and this is bizarre, but basically red goes negative here. And so you get this weird thing where there's like individual wavelengths of light, the way it hits our receptors, the way our brain processes it. You cannot match that color. The only way you can actually match that color is you have to add red to it. And then we can say, oh, this actually looks like this other color. Totally bizarre. But so they created this XYZ standard. You can convert between regular RGB and XYZ. And then on the next slide, we'll see some other more complex things. Interestingly enough, I've heard the term luminance. I didn't really understand, but basically, well, what I learned from this section is that the way you perceive brightness is primarily based on how much green you see. And so that's why in a lot of these things, it's not exactly true that green equals brightness, but it's pretty darn close. It's a first order approximation. So there's this chart, which I stared at for a long time. The individual wavelengths of light are represented on the outside here and the way you perceive them. And then everything above this triangle cannot actually be represented, which is bizarre. White is this little dot in the middle here. And then they said this is where XYZ came from, was from studying this chart. And then they had a new one, which is based on the fact that, hey, in this lower corner, you can perceive differences really, really easily. But in these other sections where you see the bigger ovals, the human eye and brain is not able to perceive differences. So if you wanted to create a scale that's sort of like uniform in, like if you add 10 to it, then it looks different, the same amount everywhere. That would not be true because down here in this lower left corner, add 10, you're gonna perceive the color difference a lot more. Up here, you add 10, and people are gonna say it's the exact same color. So that's where they came up with this L star, A star, B star. And then this is cool. I didn't know this. I thought that color cameras would have equal amounts of red, green, and blue, but actually, usually it's half green and a quarter red, quarter blue. And so the green is the most important thing. It's what you sense the most in differences in brightness. And then the red and the blue just get the shade, the chromaticity correct. I don't understand exactly if we still use gamma, we don't use gamma, but this is just because everything started with TVs and the phosphors on the TVs. The brightness is not linear response to the voltage. So if you want something that's twice as bright, you don't just give it double the input signal. So there's a conversion between, do I want to know how bright something actually looks, or do I want to know what is the value to apply to the TV to get that voltage, to get the gun to actually cause the phosphor to do its thing? So there's this gamma correction. And so apparently a lot of things are in gamma corrected values, which then totally screws things up because it's nonlinear. And then again, any transformation that you do in color or brightness space is now wrong because it's all nonlinear and all the transformations we have are linear. All right. And then they say there's other standards even on top of that. YIQ, if you ever messed with old TVs. So the more recent version of it is the Y, CBCR, sort of the same concept of brightness is highly encoded in this Y channel, and then just the blue and the red are color adjustments off of that. It mentions HSV, YXY, color ratios, little r, little g, little b, lots and lots of stuff. The final thing is compression. Dealt with a lot of these. I use JPEG files pretty much every day. It didn't go into all the gory details, but a few things that I thought were interesting is that I knew that old color TVs, the resolution of the color signal was a lot lower than the resolution of the black and white signal. So in other words, the Y actually was very compared to today, high def, no, but was many more pixels across. The default for JPEG is actually the same thing, that it does brightness at full resolution and it only does color at half resolution in both the X and the Y directions. I'm sure there's like different settings or whatever, but I had no idea. So as soon as you store it as JPEG, even at the highest quality of JPEG, you've at a minimum thrown away half of your red, or 3/4, because it's both the X and the Y direction. You've thrown away 3/4 of your red and your blue signal compared to a raw, like PNG type image. I didn't know that. And then it talks a little bit about how the compression works. And then video has some motion stuff, so that if you have objects that are moving at a constant speed, either because the camera's moving or because the object is moving, then you can kind of condense the representation of that. I think that's the last slide. Yes. All right, so whole bunch of stuff. Again, for me, the purpose of this is there's going to be a bunch of information I don't need, a bunch of information that actually will help me understand the background behind some of the things I do. And it won't be until later in my career that I'll know the difference between which of these parts that I read are the useful parts and which of the parts that I never use again. So that's why we read the whole chapter, because if I knew, then I could just tell you, oh, read chapter 1, section 1.3 and section 2.2, and you don't have to read the rest, but we don't know which ones we're going to read or not. All right. So we're actually over time. I apologize. Any final questions before we wrap up? All right. Thanks for joining today. Appreciate you guys sticking it out. So again, I will update the schedule, but the rough plan is we're doing book club the 2nd and 4th Saturdays of each month. July was a little weird because of travel, but normally the 2nd and the 4th Saturdays. So the 2nd Saturday in August, I believe it's the 9th, is our next session. We're alternating. That will be workshop 3. So much more practical, hands-on Jupyter notebooks and Python. I think training a classifier. And then 4th Saturday in August will be chapter 3 of the book. So thanks.